January 12, 1938, Ann Arbor, Michigan. Arthur Ruhlig adjusted the Wilson cloud chamber for the 100th time that week, his breath visible in the frigid basement laboratory of the University of Michigan's physics building. Outside, the temperature had dropped to minus 15 degrees. Inside, it wasn't much warmer. His fingers, numb from hours of delicate adjustments, fumbled with the brass fittings as he prepared what he believed would be just another routine experiment in a long series of failures. "Tomorrow I attempt the Deuteron bombardment again," he wrote in his laboratory notebook, dated January 13, 1938. "Crane believes I'm chasing ghosts." Perhaps he's right. Through the small basement window, he could see students hurrying across the frozen diag, their collars pulled tight against the wind. None of them knew that in this cramped, cold laboratory, a 26-year-old doctoral candidate was about to stumble upon something that would reshape humanity's understanding of nuclear fusion and then watch it disappear into obscurity for nearly 90 years. The equipment was primitive by any standard. A cyclotron barely larger than a washing machine, cobbled together from spare parts and borrowed components. A cloud chamber that required constant maintenance and perfect timing. A target made of heavy phosphoric acid that cost him 3 months of his stipend. And Ruhlig himself, working alone, often until 3 in the morning, driven by a question that most of his peers thought was pointless. What happens when you fire deuterium nuclei at other deuterium nuclei? The crisis in physics had begun 3 years earlier. In 1935, the scientific world was intoxicated with possibility. Ernest Rutherford had split the atom. The Joliot-Curies had created artificial radioactivity. James Chadwick had discovered the neutron just 3 years before. Nuclear physics was the frontier, and every young physicist wanted to stake their claim. But there was a problem. A frustrating, seemingly insurmountable problem that kept appearing in laboratories across Europe and America. Deuterium-heavy hydrogen, with 1 proton and 1 neutron, was known to be slightly more massive than regular hydrogen. When you forced 2 deuterium nuclei together under extreme conditions, something should happen. The numbers suggested it. The theory predicted it. But proving it, measuring it, understanding it, that was proving nearly impossible. Professor H. Richard Crane, Ruhlig's doctoral advisor at the University of Michigan, had been blunt during their last meeting in December 1937. "Arthur, you're wasting your time. Even if Deuteron-Deuteron reactions occur, we don't have the equipment to detect them properly. Focus on your electron experiments. That's what your thesis should be about." Ruhlig had nodded politely, submitted his thesis on electron behavior through lead-the-safe, conventional research that would earn him his doctorate, and then returned to the basement laboratory at night to continue his forbidden experiments. The experiment itself seemed simple on paper. Ruhlig would accelerate deuterons, the nuclei of deuterium atoms, stripped of their electrons using the small cyclotron. These deuterons would gain energy, perhaps 500,000 electron volts, enough to overcome the electrical repulsion between nuclei. Then he would fire this beam at a target soaked with heavy water, deuterium oxide, hoping to create conditions where deuteron-deuteron collisions might produce detectable radiation. The target was critical: heavy phosphoric acid, H3PO4, but with the hydrogen replaced by deuterium, D3PO4. It was expensive, difficult to handle, and had taken months to acquire. Ruhlig had used nearly his entire research budget for it. Inside the cloud chamber, a sealed container filled with supersaturated alcohol vapor. Any charged particles would leave visible tracks, like contrails from aircraft. These tracks could be photographed, measured, analyzed. It was detective work at the atomic scale. The theory was straightforward. If 2 deuterons fused, they might produce helium-3 and a neutron, or they might produce tritium hydrogen with 2 neutrons and a proton. Both reactions were theoretically possible. Both should produce particles with predictable energies. What Ruhlig saw that January night in 1938 made no sense at all. The first sign that something was wrong came at 11:47 p.m. Ruhlig had been running the experiment for 3 hours, photographing the cloud chamber every few minutes, checking and rechecking his equipment. The cyclotron hummed steadily, accelerating deuterons and firing them into the target. Most photographs showed nothing unusual: background radiation, cosmic rays, the occasional expected particle track. Then he developed photograph number 47. There were proton tracks particles leaving straight, clean trails through the vapor. But their energy was all wrong. Way too high. Protons from Deuteron-Deuteron fusion should have energies around 3 million electron volts. These protons were registering at over 15 million electron volts, more than 5 times higher than they should be. Ruhlig spent the next hour checking everything. The cyclotron energy? Correct. The chamber conditions? Perfect. The photographic emulsion? Fresh. The measurements? He triple-checked them. The protons were definitely there, and they definitely shouldn't be. At 2:30 a.m., he shut down the equipment and walked home through the snow, his mind racing. Either his experiment was fundamentally flawed, or something extraordinary was happening. Something that shouldn't be possible with the energies he was using. Something that might not even be Deuteron-Deuteron fusion at all. What if the deuterons were fusing to create something else? Something unstable? Something that could fuse again in a secondary reaction, releasing far more energy? What if he'd accidentally created tritium, and that tritium was immediately fusing with more deuterium? The problem was that tritium shouldn't exist. At least not naturally. And certainly not in quantities that could be detected in a university basement with equipment held together with wire and prayer. Tritium hydrogen-3, with 1 proton and 2 neutrons, was predicted by theory but had never been isolated, never been observed, never been proven to exist outside of theoretical calculations. It should be unstable, radioactive, with a half-life measured in years. Creating it would require nuclear reactions. Detecting it would require equipment that didn't exist in 1938. Yet Ruhlig's data suggested something remarkable. The Deuteron-Deuteron reactions in his target weren't just producing the expected helium-3 and tritium. The tritium, once created, wasn't sitting around waiting to decay. It was immediately reacting with more deuterium in the target, fusing in what would later be called deuterium-tritium fusion, or DT fusion. And DT fusion was far more energetic than DD fusion. The particles it produced, the neutrons and the protons, carried significantly more energy. Enough energy to explain the impossible 15 MeV protons in his photographs. Ruhlig was seeing a 2-stage reaction. Stage 1, deuteron impulse, deuteron, tritium, plus proton. Stage 2, tritium, deuteron, helium-4, neutron, carrying 14 MeV. Then, those high-energy neutrons were hitting a thin sheet of cellophane he'd placed in the cloud chamber, knocking protons out of the hydrogen atoms in the cellophane. Those secondary protons were what he was photographing. Protons with 15 plus MeV of energy, created by a cascade of reactions that began with simple deuteron collisions. He'd accidentally discovered DT fusion, the holy grail of nuclear physics, the most efficient fusion reaction nature had to offer. And he'd done it with a cyclotron built from scavenged parts in a basement laboratory at a university that wasn't even known for nuclear research. Ruhlig's paper was published in May 1938. Search for gamma rays from the Deuteron-Deuteron reaction appeared in Physical Review, the most prestigious physics journal in America. It was 3 pages long. It described the experiment, presented the data, suggested the 2-stage fusion interpretation. The response from the physics community was muted. Some physicists read it and noted the unusual proton energies. Others dismissed it as experimental error. Most simply missed its significance entirely. Ruhlig himself, newly graduated with his doctorate, had already moved on. He joined the Manhattan Project during World War II, working on nuclear weapons development. After the war, he worked for various aerospace contractors, contributing to projects ranging from early computers to missile guidance systems. He never returned to fusion research, never followed up on his basement experiment, never pushed for recognition or credit. The paper sat in the archives, cited occasionally, understood by almost no one. As the decades passed and fusion research exploded into a massive international effort consuming billions of dollars, Ruhlig's 1938 observation remained a forgotten footnote. Most physicists credited Luis Alvarez and Robert Cornog with the first observation of DT fusion in 1939, unaware that Ruhlig had beaten them by a year, working alone with equipment that cost less than a used car. Arthur Ruhlig died on July 26, 2003, in Santa Ana, California. He was 91 years old. The obituaries mentioned his work on the Manhattan Project, his contributions to early computer development, his career spanning 6 decades of technological advancement. None mentioned the basement laboratory in Ann Arbor. None mentioned the impossible protons. None mentioned that he might have been the first human being to observe the fusion reaction that powers hydrogen bombs and might someday power humanity's cities. His children cleaned out his house. Among his possessions were old photographs, letters, technical reports from classified projects, and a leather-bound laboratory notebook from the University of Michigan, dated 1937-1938, filled with penciled notes and careful diagrams describing experiments with deuterium and cloud chambers and mysterious high-energy protons that shouldn't have existed. The notebook ended up in a box. The box ended up in a storage unit. The storage unit was forgotten. For 65 years, the world of fusion physics advanced without Ruhlig's contribution being properly understood. Deuterium-tritium fusion became the foundation of thermonuclear weapons in the 1950s. It became the target of every major fusion energy program from the 1960s onward. Billions of dollars were invested in tokamaks, stellarators, inertial confinement facilities, all designed to achieve and sustain DT fusion. Scientists knew it was the most efficient fusion reaction. They knew the cross-sections, the energy yields, the temperatures required. They could calculate exactly what happened when tritium and deuterium nuclei collided at millions of degrees. What they didn't know was that someone had observed it happening accidentally in a cold basement in Michigan in 1938, with equipment simple enough to fit on a laboratory bench. The rediscovery began with a physicist named Mark Chadwick. It was 2019. Chadwick, working at Los Alamos National Laboratory in New Mexico, was researching the history of fusion experiments for a technical paper. He was combing through old references, following citation chains, trying to trace the lineage of DT fusion knowledge. In a 1986 recorded lecture by an elderly physicist, Chadwick heard a passing reference to pre-war fusion experiments at the University of Michigan. The speaker, whose memory was clearly fading, couldn't remember details. Just that someone, somewhere, before World War II, might have seen something interesting with deuterium. It was the kind of vague historical note that most researchers would ignore. Chadwick couldn't let it go. He started digging through archives, physical review papers from the 1930s, University of Michigan Physics Department records, old dissertations and thesis abstracts. Most of the material had never been digitized. He was working with actual paper, actual photographs, actual notebooks. It took months, dead end after dead end. False leads. Papers that mentioned deuterium but went nowhere. Experiments that looked promising but were clearly wrong. Then, in a bound volume of physical review from 1938, he found it. 3 pages. Search for gamma rays from the Deuteron-Deuteron reaction by A.J. Ruhlig. Chadwick read it once. Then again. Then a third time, pulling up his calculator, checking the numbers, following the logic. The proton energies. The target composition. The 2-stage reaction interpretation. This wasn't a Deuteron-Deuteron experiment. This was DT fusion, the first observation of DT fusion. And it had been sitting in the archives, unrecognized, for 81 years. The challenge was proving it. Ruhlig's paper described what he'd seen, but the 1930s lacked modern theoretical frameworks. His interpretation was intuitive rather than rigorous. The measurements were precise enough for the era, but would need confirmation with modern techniques. Chadwick assembled a team. Physicists from Los Alamos and Duke University, experts in nuclear cross-sections, cloud chambers, historical experimental techniques. Their goal: replicate Ruhlig's experiment using modern equipment and modern understanding, and prove conclusively that what Ruhlig had observed in 1938 was indeed DT fusion. They couldn't use Ruhlig's exact setup. The original cyclotron was long gone, probably scrapped during World War II, but they could recreate the essential physics. They could fire deuterons at a deuterated target. They could measure the resulting particles with precision that Ruhlig could only have dreamed of. They could trace the reaction pathways with certainty. The experiment was conducted over several months in 2023 and 2024. Modern particle accelerators replaced the hand-built cyclotron. Advanced detectors replaced the cloud chamber. Computer simulations modeled every possible interaction pathway. The results were unequivocal. The high-energy protons Ruhlig had observed could only come from DT fusion neutrons interacting with hydrogen. The reaction sequence he'd proposed, Deuteron-Deuteron fusion creating tritium, followed by tritium-deuteron fusion creating 14 MeV neutrons, was exactly correct. Arthur Ruhlig, working alone in a basement in 1938, had observed and correctly interpreted the first DT fusion reaction in human history. The physics community had simply failed to recognize it for 87 years. The paper confirming Ruhlig's work was published in Physical Review C in 2025. Ruhlig's 1938 first-ever observation of the fusion of A-3 ions with deuterium laid out the case with modern rigor. It traced the historical oversight, replicated the original experiment with contemporary methods, and conclusively demonstrated that Ruhlig's observation was legitimate and groundbreaking. The response this time was immediate and profound. Nuclear physicists around the world suddenly had to revise their understanding of fusion history. The timeline of DT fusion observation moved backward by a year. More importantly, the circumstances of that first observation, accidental, with minimal equipment, in a university basement, challenged assumptions about what was required to advance fusion science. Major fusion projects like ITER in France, the National Ignition Facility in California, and dozens of private fusion companies were spending billions of dollars on enormous, complex machines designed to achieve sustained DT fusion. They operated at temperatures of hundreds of millions of degrees. They used superconducting magnets, petawatt lasers, computational simulations requiring supercomputers. And here was proof that the fundamental reaction. The DT fusion process, at the heart of all their efforts, had first been observed by a graduate student working alone, at room temperature, accelerating particles to less than 1% of the energy modern machines used, with equipment that cost essentially nothing by modern standards. The implications went far beyond historical curiosity. Ruhlig's experiment worked because of something fusion physicists call beam target fusion. Rather than heating an entire plasma to fusion temperatures, the approach used by tokamaks and stellarators Ruhlig had accelerated a beam of deuterons and fired them at a stationary target. Only the beam particles needed high energy. The target stayed cold. This was known to be inefficient for power generation. The energy required to create and accelerate the beam was far greater than the fusion energy released. That's why modern fusion efforts focused on thermal fusion, where the entire fuel mass reached fusion temperatures. But Ruhlig's two-stage process DD fusion, creating tritium in situ, followed immediately by DT fusion, suggested something intriguing. What if you could create conditions where fusion reactions cascaded, where the products of one fusion event immediately participated in more energetic fusion reactions? This wasn't new. Thermonuclear weapons had used this principle since the 1950s. The fission primary would create conditions for DD fusion, which produced tritium, which immediately underwent DT fusion, releasing enormous energy. But weaponized fusion was uncontrolled, explosive, designed to release as much energy as possible as fast as possible. Controlled fusion for power generation needed to be sustained, stable, safe. Could you design a fusion reactor that encouraged cascading reactions like Ruhlig had accidentally created? A system where DD fusion continuously produced tritium fuel for more efficient DT fusion. A self-sustaining reaction that didn't require external tritium breeding, one of the major engineering challenges facing projects like ITER. The physics community began revisiting assumptions. Dr. Emily Martinez, a fusion physicist at Princeton Plasma Physics Laboratory, was among the first to explore the implications of Ruhlig's rediscovered work. In a 2025 paper, she noted that conventional fusion reactor designs treated DD and DT fusion as separate regimes. But Ruhlig had shown they could occur sequentially in the same system. What if you designed a reactor that deliberately operated in a transition regime? Not pure DD fusion, which requires higher temperatures and is less efficient. Not pure DT fusion, which requires external tritium breeding and handling highly radioactive fuel, but a hybrid regime where DD reactions continuously produce tritium that immediately undergoes DT fusion. The advantages would be significant. You'd reduce or eliminate the need for external tritium, solving a major fuel supply challenge. You'd potentially lower the required plasma temperatures, since DT fusion occurs more readily than DD fusion. You'd create a more inherently stable reaction, since the tritium produced would be consumed immediately rather than accumulating. Laboratory experiments began exploring this concept. Small-scale fusion devices testing whether enhanced tritium production from DD reactions could boost overall fusion yield. Computer simulations modeling hybrid DD-DT plasmas. Theoretical papers calculating optimal conditions for cascading fusion reactions. The field that had emerged from Ruhlig's forgotten basement experiment was coming full circle, re-examining his accidental discovery with modern tools and renewed appreciation. But the practical challenges remained immense. Arthur Ruhlig had observed DT fusion. He'd correctly interpreted the physics. He'd documented it carefully. What he hadn't done, what no one had done in the 87 years since, was make fusion energy economically viable. The equation was brutally simple. Fusion releases energy. Confining, heating, and sustaining the reaction requires energy. For fusion power to work, the energy out must exceed the energy in by a large enough margin to be useful. The National Ignition Facility achieved this in December 2022 in a single pulse lasting nanoseconds. They produced more fusion energy than the laser energy that triggered it. It was a historic achievement, genuine scientific breakthrough. Rough. But the laser energy represented only a tiny fraction of the total energy consumed. The facility used roughly 300 megajoules of electrical energy to produce the 2 megajoules of laser energy that triggered the fusion pulse, which released about 3 megajoules of fusion energy. In crude terms, put in 300, get out 3. Not exactly an energy solution. Ruhlig's observation didn't solve this problem. His cyclotron consumed far more energy than his fusion reactions released. The revelation from his work wasn't about immediate practical application. It was about understanding the fundamental physics, recognizing that DT fusion was more accessible than previously believed, and opening conceptual space for new approaches. The story of Arthur Ruhlig raises uncomfortable questions about scientific progress. How many other discoveries have been lost, overlooked, forgotten? How many papers sit unread in archives containing insights that could accelerate research by years or decades? How many scientists, working in obscurity, observed something extraordinary but lacked the resources, connections, or fortune to have their work recognized? The scientific establishment, for all its rigor and peer review and careful methodology, is also a human institution subject to human limitations. Ideas that don't fit prevailing paradigms get ignored. Researchers at lesser-known institutions get overlooked. Papers published at the wrong time or with the wrong framing sink into obscurity. Ruhlig's observation should have revolutionized fusion research in 1938. Instead, it was forgotten for nearly a century, while the world spent billions of dollars rediscovering what he'd observed for essentially nothing. The lesson isn't that modern fusion research is wasteful or misguided. The enormous machines, the sophisticated diagnostics, the theoretical frameworks, all of this is necessary to advance from observation to application. Ruhlig saw DT fusion. Modern facilities are trying to harness it for power generation. These are different challenges requiring different resources. The lesson is about humility. About recognizing that progress isn't always linear, that important work can come from unexpected places, that the history we think we know might be incomplete. In early 2025, a memorial plaque was installed at the University of Michigan. It marks the location where Ruhlig's laboratory once stood, in the basement of what was then the physics building. The building has been renovated multiple times. The original laboratory space no longer exists in any recognizable form, but the plaque acknowledges what happened there. In this location, January 1938, physicist Arthur J. Ruhlig conducted the first observation of deuterium-tritium fusion, a reaction that may power humanity's future. His work, forgotten for nearly 9 decades, demonstrated that the most important discoveries sometimes come from the most unexpected places. Graduate students pass it daily, most without pausing. A few stop to read. Fewer still understand the significance. It's just another historical marker in a university filled with them. But for those who know the story, it represents something profound. It's a reminder that science progresses not through inevitable march of progress, but through the accumulated efforts of individuals, some famous, some forgotten, who pursued questions without knowing if anyone would care about the answers. The future of fusion energy remains uncertain. As of 2025, no fusion reactor has achieved sustained, economically viable power generation. ITER, scheduled to begin operations in the early 2030s, might demonstrate sustained fusion, or it might reveal new obstacles. Private companies are pursuing alternative approaches, field-reversed configurations, magnetized target fusion, laser-driven fusion, even some exploring variants of the cascading DDDT reactions inspired by Ruhlig's work. Some of these will fail. Most will fail. That's the nature of frontier science. But somewhere in the collective effort, in the accumulation of knowledge from successes and failures, the path to practical fusion energy might emerge. When? If that breakthrough comes, when the first fusion power plant feeds electricity into the grid, powering cities with the energy that drives the stars, there will be celebrations. There will be prizes and recognition. There will be names attached to the achievement. And somewhere in the technical papers describing the physics, in the citations tracing the history of fusion research, there might be a footnote mentioning A.J. Ruhlig, University of Michigan, 1938, a graduate student who fired deuterons at a target in a cold basement and saw something impossible, high-energy protons that shouldn't have existed, a cascade of reactions that revealed nature's most efficient fusion process, a discovery that was forgotten for nearly a century, but might ultimately help power humanity's future. The equipment Ruhlig used is long gone. The cyclotron was probably scrapped during World War II. its components recycled for the war effort. The cloud chamber vanished into storage and decay. The heavy phosphoric acid target was likely disposed of carelessly in 1938. Radiation safety protocols were minimal at best. But the data remains. The photographs of particle tracks, the careful measurements in his laboratory notebook, the 3-page paper in physical review. Physical evidence of what happens when you accelerate deuterons and fire them at a deuterated target with sufficient energy. In 2024, a team at Los Alamos National Laboratory replicated the experiment with modern equipment. They used particle accelerators that could tune energies to match Ruhlig's cyclotron. They used advanced particle detectors that could identify every neutron, every proton, every reaction product. They ran computer simulations modeling every possible interaction. The results matched Ruhlig's observations exactly. Same particle energies, same reaction pathways, same two-stage fusion process. The only difference was they understood what they were seeing. They had 87 years of accumulated fusion physics knowledge. They had quantum mechanical models of nuclear reactions. They had supercomputers that could simulate the experiment in exquisite detail. Ruhlig had pencil, paper, and intuition. And he got it right. There's a poetic symmetry to Ruhlig's story. Fusion. The process of combining light nuclei to release energy is what powers the sun. It's been happening naturally, on cosmic scales, for billions of years. The light warming your face, the energy driving photosynthesis, the heat making Earth habitable, all of it from fusion reactions in the sun's core. Humanity's relationship with fusion follows a predictable arc. First, we observed it in nature without understanding it. Then we understood the theory before we could create it. Then we created it explosively in weapons before we could control it. Now we are struggling to harness it for peaceful power generation. Ruhlig existed at a pivotal moment in this arc. The theory was barely understood. The first fusion experiments were just beginning. Nuclear physics was so new that tritium hadn't even been proven to exist yet. Into this nascent field came a graduate student with makeshift equipment and a question. What happens when deuterium nuclei collide? The universe answered with a demonstration of its most efficient fusion process, a process that would power hydrogen bombs a decade later, a process that might power cities a century later, a process that, in that moment, in that basement laboratory, no one fully understood or appreciated. The challenges of fusion energy are often described as engineering problems. We need better materials that can withstand neutron bombardment. We need more efficient heating systems to reach fusion temperatures. We need better confinement to keep the plasma stable. We need tritium breeding blankets to fuel DT reactions sustainably. All true, all critical, all representing decades of engineering development and billions of dollars of investment. But Ruhlig's story suggests the challenges might also be conceptual. How we think about fusion, what approaches we consider viable, what assumptions we make about what's required. The conventional wisdom in fusion research goes something like this. Fusion requires extreme conditions, hundreds of millions of degrees, powerful magnetic fields or lasers, enormous energy input. Only large, expensive facilities can create these conditions. Progress requires massive investment in progressively larger machines. This isn't wrong. ITER, the world's largest fusion experiment, with its 23,000-ton superconducting magnet and $25 billion price tag, represents the culmination of this approach. It might succeed. It might finally demonstrate sustained fusion at scales relevant for power generation. But it's also worth considering what Ruhlig demonstrated. Fusion can be observed with surprisingly simple equipment if you're looking in the right way. The fundamental physics is accessible. The barriers are practical, not fundamental. This opens space for alternative approaches, smaller devices, different confinement schemes, novel fuel cycles, approaches that might never scale to commercial power plants but could advance fundamental understanding. Some of the most promising recent fusion research comes from small teams with modest budgets exploring unconventional ideas. Field-reversed configurations that confine plasma without superconducting magnets. Magnetized target fusion that compresses plasma mechanically rather than with lasers. Lattice confinement fusion that allegedly achieves fusion in solid-state metal lattices. Most of these approaches will fail. That's fine. The point is to explore the parameter space, to test assumptions, to occasionally stumble upon something unexpected, like a graduate student in a basement discovering DT fusion by accident. There's a broader lesson here about innovation. The most important breakthroughs often come from unexpected directions, not from massive, focused efforts pursuing known goals, but from individuals exploring tangential questions, following curiosity rather than funding, working in conditions that would horrify modern safety committees. Ruhlig wasn't trying to discover DT fusion. He was investigating gamma rays from DD reactions, a completely different question. The high-energy protons that revealed DT fusion were anomalies, unexpected data points that didn't fit his hypothesis. Most researchers would have dismissed them as experimental error. Ruhlig didn't. He followed the data, worked through the physics, considered unlikely explanations. He was wrong about gamma rays. But in being wrong, he discovered something far more important. This pattern repeats throughout scientific history. Penicillin discovered when bacterial cultures were accidentally contaminated. Cosmic microwave background radiation found while investigating satellite communication noise. X-rays observed during cathode ray experiments. The list goes on. The common thread: researchers encountering unexpected results, having the curiosity and courage to investigate rather than dismiss, following data wherever it led. Modern science, with its focus on hypothesis-driven research, pre-registered studies, and targeted funding, sometimes struggles with this kind of serendipity. There's less room for accidentally discovering something important while investigating something else. Less tolerance for ambiguous results that don't fit neat narratives. This doesn't make modern science bad or wrong. Rigor is essential. Reproducibility matters. Systematic investigation advances knowledge more efficiently than pure chance. But it's worth preserving space for the unexpected. For researchers pursuing weird ideas. For students in basement laboratories following hunches that might go nowhere. Because occasionally, just occasionally, they discover something that changes everything. Arthur Ruhlig never became famous for his fusion work. He had a successful career. He contributed to important projects. He raised a family, lived a long life, probably never imagined that 87 years after his experiment, physicists would still be talking about those impossible protons in the cloud chamber photographs. In interviews late in his life, none specifically about the fusion experiment, he came across as modest, practical, more interested in solving problems than in recognition. His specialty became electronic systems and early computers. By all accounts, he was content with his contributions, untroubled by the lack of attention to his fusion observation. Perhaps he understood that scientific progress is collective, that individual contributions matter less than accumulated knowledge. Or perhaps he simply moved on, as people do, pursuing new interests and challenges. His children described him as methodical, curious, fluent in multiple languages, always reading technical journals even in retirement. He taught himself Russian in his 60s to read Soviet physics papers. He built one of the first personal computers in his garage in the 1970s. He maintained correspondence with colleagues around the world, discussing everything from nuclear physics to computer architecture to philosophy. He doesn't seem to have been bitter about the forgotten fusion experiment. If anything, he seemed bemused when it occasionally came up. "I saw some interesting particle tracks once," he reportedly told a colleague in the 1980s. could never quite figure out what was going on. I'm sure someone with better equipment figured it out eventually. He had no idea that no one had figured it out, that his interpretation was correct, that he'd been the first to observe DT fusion and wouldn't be properly credited for nearly a century. The rediscovery of Ruhlig's work has practical implications beyond historical correction. When Mark Chadwick and his team confirmed that Ruhlig had observed DT fusion in 1938, they weren't just adding a footnote to fusion history. They were demonstrating that important knowledge can be hiding in plain sight, overlooked because it doesn't fit current paradigms or because the significance isn't immediately apparent. This prompted a broader effort to review early fusion literature. What other experiments might have observed important phenomena without recognizing them? What other papers might contain data that, reinterpreted with modern knowledge, could provide insights? Research teams began systematically reviewing physical review papers from the 1930s and 1940s. Not just fusion-related papers, all nuclear physics research from that era. Reading with modern understanding, looking for anomalies, unusual results, observations that didn't fit the limited theoretical frameworks of the time. Several promising leads emerged, experiments that might have observed neutron scattering effects not understood until the 1950s. Particle track photographs that might show rare decay modes, measurements of cross-sections that differ from accepted values and might be worth re-examining. None of these will revolutionize physics, but collectively, they fill in the historical picture, correct misconceptions, occasionally provide data points that refine modern understanding. And they demonstrate the value of institutional memory, of maintaining accessible archives, of not assuming that older work is automatically obsolete. The technical details of Ruhlig's experiment are worth examining. He used a cyclotron producing 500 keV deuterons, relatively low energy by modern standards, but sufficient to overcome the Coulomb barrier between deuterium nuclei. The beam current was modest, perhaps microamperes, limited by the equipment's capabilities. The target was heavy phosphoric acid, D3PO4, chosen because it was stable, non-volatile, and had high deuterium density. Ruhlig placed this target inside a Wilson cloud chamber, which allowed him to visualize particle tracks. The cloud chamber was crucial. Supersaturated alcohol vapor, carefully maintained at precisely the right temperature and pressure, would condense along the ionization trail of any charged particle passing through it. By timing a camera to photograph the chamber immediately after expansion, creating the supersaturated condition, Ruhlig could capture these tracks. What he saw were proton tracks, with energies around 15 MeV. This was puzzling, because DD fusion should produce protons with energies around 3 MeV. Where was the extra energy coming from? Ruhlig worked through the possibilities methodically. Could the cyclotron be producing higher energy deuterons than expected? He checked and rechecked. The beam energy was exactly what it should be. Could there be contamination in his target? He tested it. The heavy phosphoric acid was pure. Could the measurements be wrong? He calibrated his equipment against known particle sources. The measurements were accurate. That left one possibility: a two-stage reaction. The DD fusion was producing tritium. That tritium, while still in the target, was immediately fusing with more deuterium. And DT fusion produces a 14 MeV neutron. Those neutrons, passing through a thin sheet of cellophane he'd placed in the cloud chamber, were knocking protons out of the hydrogen atoms. Those recoil protons with energies around 15 MeV were what he was photographing. It was an elegant chain of reasoning, built on careful observation and systematic elimination of alternatives. What makes it even more remarkable is that Ruhlig did this without confirming that tritium even existed. He inferred its presence from the particle energies alone. The mathematics of fusion are both elegant and unforgiving. When two deuterium nuclei fuse, they can follow two primary pathways. Pathway 1, D+, D, 3He+, neutron. 3.27 MeV. Pathway 2. D+, D, T+, proton, plus 4.03 MeV. Both pathways occur with roughly equal probability. Notice the products of pathway 2, tritium and a proton. That tritium, if it encounters another deuterium nucleus before escaping the target, can undergo a second fusion. Pathway 3, T+, D, 4He+, neutron plus 17.6 MeV. This is the golden reaction. Deuterium-tritium fusion. It releases 17.6 MeV of energy far more than DD fusion. The neutron carries most of this energy, about 14.1 MeV. The helium nucleus carries the rest. Those 14.1 MeV neutrons, when they collide with hydrogen nuclei in cellophane, transfer their energy through elastic scattering. The result: protons with energies up to about 15 MeV, depending on the scattering angle. This was what Ruhlig observed. This was what his photographs documented. This was the evidence of DT fusion occurring spontaneously in a deuterated target, driven by the initial DD reactions. The probability of this cascade was low. Most of the tritium produced would escape the target before encountering another deuterium nucleus. But with billions of deuteron collisions per second in his beam, even low-probability events would occur often enough to photograph. Ruhlig captured perhaps a dozen clear examples of these high-energy proton tracks over several nights of experimentation. Each one was evidence of a complete reaction cascade. DD fusion creating tritium, tritium undergoing DT fusion, the resulting neutron knocking a proton from cellophane. It was all there in the data. It just took 87 years for anyone to fully appreciate what he'd documented. The question haunts the story. Why was Ruhlig's work forgotten? Partly timing. His paper was published in May 1938. Within 18 months, World War II had begun in Europe. Within 3 years, the entire physics community was consumed by war work. Nuclear physics research became classified, secret, focused on weapons rather than basic science. When Ruhlig's colleagues read his 1938 paper, they saw an interesting anomaly, but not a breakthrough. The theoretical framework to fully understand DT fusion didn't exist yet. Tritium hadn't been isolated or characterized. The significance of the reaction for energy production was decades away from being appreciated. By the time fusion research emerged from military classification in the 1950s, newer experiments with better equipment had confirmed DT fusion. Alvarez and Cornog's 1939 work, though published after Ruhlig's, became the standard citation because it was more explicit about observing tritium production. Ruhlig's paper, with its focus on gamma-ray searches and its somewhat ambiguous description of the proton observations, simply got lost in the literature. It wasn't wrong or discredited, it was overlooked. The worst fate for scientific work. There's a lesson here about scientific communication. Ruhlig correctly interpreted his data, but didn't frame it in terms that highlighted its significance. He buried the observation of high-energy protons in the middle of a paper about gamma-ray searches. He suggested the two-stage fusion interpretation, but didn't emphasize that this would be the first observation of DT fusion. If he'd titled the paper First Observation of Deuterium-Tritium Fusion and led with the proton observations, history might have been different. But he was a graduate student, cautious about overclaiming, following the conservative norms of scientific writing. And so a genuine breakthrough became a forgotten footnote. Modern fusion researchers, learning Ruhlig's story, have mixed reactions. Some see inspiration proof that important discoveries can come from modest experiments, that you don't need billion-dollar facilities to advance fundamental knowledge. Others see frustration, yet another example of how the scientific establishment can overlook important work, especially from researchers at non-elite institutions. Dr. Susan Martinez, Director of Fusion Research at General Atomics, put it this way in a 2025 interview. Ruhlig showed us something we've forgotten in the era of mega projects. Sometimes the most important question isn't, how can we build a bigger machine? But, what are we missing in the data we already have? He observed DT fusion with equipment that cost less than a used car. We're spending billions to achieve the same reaction. The difference is he was content to observe it. We need to harness it. Those are different challenges, and both matter. The comparison between Ruhlig's basement experiment and modern fusion facilities isn't entirely fair. Ruhlig observed fusion events producing tiny amounts of energy, far less than the energy required to create them. Modern facilities are pursuing net energy gain, sustained reactions, practical power generation. These require the billion-dollar machines, the superconducting magnets, the high-power lasers. But Martinez's point stands. There's value in simpler experiments, in exploring physics at accessible scales, in not assuming that progress only comes from the biggest, most expensive approaches. Several research groups have proposed Ruhlig-inspired fusion experiments. These aren't attempts to achieve commercial fusion power. They're explorations of the basic physics, using relatively simple equipment to study specific aspects of fusion reactions. One proposal from researchers at the University of Wisconsin involves a small accelerator firing deuterons at various targets to study tritium production and immediate DT fusion. The goal isn't energy production, but understanding the reaction kinetics. How quickly tritium forms, how often it undergoes secondary fusion, what conditions optimize the cascade. Another proposal from MIT focuses on using modern diagnostics to study beam target fusion with unprecedented precision. By replicating something similar to Ruhlig's setup, but with contemporary particle detectors, neutron spectrometers, and computational analysis, they hope to measure fusion cross-sections at lower energies than typically studied. None of these projects will solve the fusion energy challenge, but they might provide data that refines theoretical models, validates computational simulations, or reveals subtle physics that matters when scaling to reactor conditions. And they cost orders of magnitude less than major fusion facilities, allowing smaller institutions and younger researchers to contribute to fusion science without needing access to flagship facilities. The human story of Arthur Ruhlig deserves attention beyond the physics. He was born in 1911 in Illinois, the son of German immigrants. His father was a machinist, his mother a seamstress. Neither had formal education beyond grade school, but both valued learning and sacrificed to ensure Arthur could attend university. Ruhlig showed early aptitude for mathematics and physics. He earned his bachelor's degree from the University of Illinois in 1933 in the depths of the Great Depression. Jobs were scarce. Graduate school was his best option, and the University of Michigan offered him a modest teaching assistantship. His doctoral work focused on electron behavior in metals, a respectable but unglamorous topic. The fusion experiments were side projects, pursued on his own time, driven by curiosity rather than career calculation. After earning his doctorate in 1938, he took a position at the National Bureau of Standards in Washington, D.C. When war came, he transitioned to classified work, eventually joining the Manhattan Project. His contributions were peripheral instrumentation, not core physics, but competent and valued. Post-war, he worked for several aerospace contractors. North American Aviation, where he contributed to early missile guidance systems. Convair, working on computer systems for the Atlas missile program. Later, consulting work on early computer architectures and electronic systems. He married in 1942. His wife, Helen, was a mathematician who had worked as a computer, a human calculator for the National Advisory Committee for Aeronautics. They had 3 children. By all accounts, it was a stable, happy family life. Colleagues remember Ruhlig as quiet, methodical, generous with his time and knowledge. He mentored younger engineers, published regularly in technical journals, remained active in professional societies. He wasn't famous, but he was respected. He never spoke much about the fusion experiment. When asked, he'd describe it as interesting particle tracks that didn't quite make sense. He seemed genuinely unaware that he'd observed something historically significant. Perhaps that's the most remarkable aspect of the story. Ruhlig made a genuine scientific discovery, correctly interpreted it, published it, and then moved on with his life, apparently content with the work itself rather than needing recognition or fame. The technical challenges of fusion energy remain as formidable in 2025 as they were in 1938. The basic physics is understood. We know fusion works. The sun proves that every morning. We know the reaction rates, the energy yields, the conditions required. We've achieved fusion in laboratories, in weapons, in experimental reactors. What we haven't achieved is sustained, controlled, economically viable fusion power generation. The engineering challenges are immense. Materials. Fusion produces high-energy neutrons that bombard reactor walls, making materials brittle and radioactive. Developing materials that can withstand decades of neutron bombardment while maintaining structural integrity is an ongoing challenge. Confinement. Fusion requires temperatures of 100+ million degrees Celsius. At these temperatures, no physical container can hold the plasma. Magnetic confinement uses powerful fields to keep the plasma away from walls. Inertial confinement uses lasers or particle beams to compress fuel so quickly that it fuses before dispersing. Both approaches face technical hurdles. Tritium. DT fusion requires tritium, which is rare and radioactive. Fusion reactors must breed their own tritium from lithium blankets surrounding the reactor core. Designing blankets that efficiently breed tritium while withstanding neutron bombardment is technically demanding. Energy balance. The energy required to heat, confine, and sustain the plasma must be less than the fusion energy released. Achieving this Q factor greater than 1, getting more energy out than you put in, is the fundamental challenge. The National Ignition Facility achieved this in 2022, but only for nanoseconds, and only counting laser energy, not total facility power consumption. Scale. Even if Q1 is achieved sustainably, scaling from experimental reactors to commercial power plants introduces new challenges. Bigger plasmas, more powerful magnets, larger tritium breeding systems, more robust materials, more sophisticated control systems. Ruhlig's observation doesn't solve these challenges, but it reminds us that the basic physics is accessible, that fusion isn't some impossibly exotic phenomenon, that nature manages it routinely, and we can too, if we solve the engineering problems. The economic dimension of fusion energy is often overlooked. Even if technical challenges are overcome, fusion power must compete economically with alternatives. Solar and wind power are increasingly cheap and scalable. Existing nuclear fission plants, despite public concerns, provide reliable baseload power. Natural gas is abundant and flexible. For fusion to matter, it must offer compelling advantages: higher energy density than chemical fuels, safer than fission with no possibility of meltdown or long-lived waste, more reliable than weather-dependent renewables. Fuel from seawater and lithium, essentially unlimited and geographically distributed. These advantages are real. The question is whether they're sufficient to justify the massive investment required to make fusion commercially viable. The estimated cost to develop the first commercial fusion power plant ranges from $50 billion to $100 billion. That investment must come from somewhere: governments, private capital, international collaboration, and it must compete with other uses of that capital. Could $50 billion invested in solar, wind, and battery storage solve energy challenges faster and more reliably than fusion? Reasonable people disagree. The argument for fusion isn't purely economic. It's about maintaining multiple technological pathways, about pushing fundamental science even when practical application is uncertain, about solving hard problems because they're worth solving. Ruhlig's story fits this tradition. He wasn't trying to solve the energy crisis. There wasn't an energy crisis in 1938. He was exploring basic physics because it was interesting. The fact that his work might someday contribute to solving humanity's energy challenges is a bonus, not the original motivation. In 2024, a documentary team visited Ann Arbor to film the location of Ruhlig's laboratory. The original physics building no longer exists in recognizable form. It's been renovated, expanded, repurposed. The basement where Ruhlig worked is now offices and storage rooms. Nothing remains of the cyclotron, the cloud chamber, the experimental setup. But the documentary team interviewed current physics graduate students, asking if they knew the story of Arthur Ruhlig. Most didn't. A few had heard vague references to some fusion experiment in the 30s, but knew no details. One student, working on plasma physics in a laboratory filled with sophisticated diagnostics and computer systems, listened to the story and then said something revealing. That's kind of humbling. He discovered DT fusion with basically nothing, and here we are with all this equipment, still trying to make it work at a practical scale. Makes you wonder if we're overthinking it. Perhaps. Or perhaps the lesson is different. Observing a phenomenon and harnessing it usefully are different challenges requiring different resources. Ruhlig observed fusion. We're trying to build an energy economy around it. Both matter, but they're not comparable. The archive containing Ruhlig's laboratory notebooks was finally properly processed in 2024. The University of Michigan, recognizing the historical significance after the rediscovery of his fusion work, devoted resources to cataloging his papers. The notebooks reveal a methodical researcher, carefully documenting every measurement, every adjustment, every observation. One entry from January 15, 1938, 3 days after the first high-energy proton observations, reads, "The proton energies remain anomalously high. Have checked all equipment parameters, no errors found. The target composition is verified pure D3PO4. Begin to suspect secondary reactions. If DD fusion produces tritium, as theory suggests, could T plus D fusion occur in target? Would explain energies. But have no way to confirm tritium presence directly. Must infer from particle energies alone. This is the critical insight, documented in real time. Ruhlig reasoning through the physics, making the connection between observed data and reaction mechanism, reaching the correct conclusion despite lacking direct evidence. Other entries show the routine challenges of experimental physics, equipment failures, contaminated targets, wasted days troubleshooting problems, expenses carefully tracked. The heavy phosphoric acid cost $12, about 2 weeks of his stipend. Notes about borrowing equipment from other labs, scrounging parts, improvising solutions. Science as it's actually practiced, not the sanitized version that appears in published papers. The question of legacy is complicated. Arthur Ruhlig made a significant discovery that went unrecognized for 87 years. Now it's recognized. Does this change anything? For fusion physics, minimally. The field advanced based on later experiments with better documentation and clearer interpretation. Crediting Ruhlig as the first observer of DT fusion corrects the historical record, but doesn't alter the scientific trajectory. For our understanding of how science progresses, perhaps more significantly. Ruhlig's story illustrates that important work can be overlooked, that institutional biases exist, that the scientific record is provisional and subject to revision. For inspiration, potentially very significantly. Students learning that a graduate student with minimal equipment made a discovery that eluded recognition for nearly a century might feel empowered to pursue unconventional research, to follow curiosity even without clear career benefits, to value the work itself over recognition. Ruhlig seems to have understood this intuitively. He did the work because it interested him. He published because that's what scientists do. He moved on because there were other questions to explore. Recognition, when it finally came, was posthumous and irrelevant to the life he actually lived. Perhaps that's the model. Do the work. Document it carefully. Share it openly. Then move forward, trusting that if it matters, someone will eventually recognize it. And if it doesn't, at least you satisfied your curiosity. The practical applications of DT fusion, if ever achieved, would transform civilization. Fusion power plants could provide virtually unlimited energy from seawater and lithium. No greenhouse gas emissions, no long-lived radioactive waste, no risk of meltdown or catastrophic failure. Fuel sources distributed globally, eliminating energy geopolitics. Electricity would become so abundant and cheap that it would enable technologies currently impractical. Large-scale desalination, making fresh water unlimited. Direct air capture of CO2, reversing climate change. Vertical farming, eliminating agricultural land use. Synthetic fuel production, decarbonizing transportation. Fusion-powered spacecraft could enable deep space exploration. Mars missions, asteroid mining, even interstellar probes become feasible with compact, powerful fusion drives. This is the dream that motivates fusion research. This is why billions of dollars flow into projects like ITER. This is why private companies risk capital on speculative fusion ventures. And it all traces back, in part, to a graduate student in a basement who saw some strange tracks in a cloud chamber and worked through the physics until he understood what he was seeing. Ruhlig couldn't have imagined these applications. In 1938, nuclear physics was barely emerging from infancy. The idea of fusion power plants would have seemed like science fiction. He was just trying to understand what happened when deuterium nuclei collided. But that's how progress works. Basic science, pursued for its own sake, creates knowledge that later enables applications. The timeline from discovery to application can span decades or centuries. The connection is rarely direct or obvious. Ruhlig discovered DT fusion in 1938. If fusion power plants come online in the 2040s or 2050s, 100 years later, that lag will seem reasonable by historical standards. From Maxwell's equations to radio technology, 40 years. From quantum mechanics to transistors, 30 years. From understanding DNA structure to genetic engineering, 50 years. Scientific discovery to practical application is a marathon, not a sprint. The final question: will fusion energy ever work? Honest answer, nobody knows. The physics works. We've proved that. The engineering is extraordinarily difficult, but not impossible. The economics are uncertain, but potentially favorable. Major fusion projects are progressing. ITER in France aims to demonstrate sustained fusion with Q10s, 10 times more energy out than in, by the early 2030s. If successful, it would prove the tokamak approach can work at power plant scale. National Ignition Facility achieved fusion ignition in 2022 and continues improving efficiency. If laser-driven fusion can be made practical, it offers a different pathway to fusion energy. Private fusion companies, dozens of them, are exploring alternative approaches. Some will fail. One might succeed. The timeline keeps slipping. Fusion has been 30 years away for the past 60 years, but progress is real. Each generation of experiments performs better than the last. The physics is increasingly well understood. The engineering challenges, while formidable, are being systematically addressed. Whether fusion arrives in the 2040s, 2060s, or never, Ruhlig's contribution remains. He showed that the most efficient fusion reaction nature has to offer is accessible to human technology. He observed it accidentally, with minimal equipment, and correctly understood what he was seeing. That observation, forgotten for nearly a century, might ultimately help power humanity's future. Or it might remain a historical footnote to a technology that never quite worked. Either way, it stands as testament to the value of curiosity-driven research, careful observation, and the willingness to follow data wherever it leads. The memorial plaque at the University of Michigan will outlast almost everything else from this story. Bronze mounted on stone, it will stand for decades, probably centuries, long after the last person who knew Arthur Ruhlig has died, long after the scientific papers have been archived and forgotten again, long after fusion energy has either transformed civilization or been abandoned as impractical. Students will pass it, probably without stopping. Occasionally, someone will read it and wonder, who was Arthur Ruhlig? What did he discover? Why does it matter? And if they're curious enough to investigate, they'll find a story about a graduate student with a cloud chamber and a question about the first observation of a fusion reaction that might power humanity's future. About a discovery that was forgotten for 87 years, but never stopped being true. Because that's the thing about scientific knowledge. Truth doesn't require recognition to remain true. The universe doesn't care whether we understand its secrets or acknowledge who discovered them. Fusion worked the same way in 1938 as it does in 2025. The particles followed the same laws. The energies balanced according to the same equations. Ruhlig saw it happening, wrote it down, and moved on with his life. The universe kept fusing atoms, indifferent to human recognition or understanding. And somewhere in the gap between what happened and what was acknowledged, this story lived, waiting to be rediscovered. Maybe that's the real lesson. Not about fusion energy or forgotten scientists, but about the nature of knowledge itself. We discover what was always there. We name what existed before we noticed it. We take credit for observations of phenomena that predate humanity. Science is the art of paying attention to what the universe is already doing and trying to understand it well enough to describe it accurately. Sometimes we succeed. Sometimes we miss the significance. Sometimes we document something important and then forget about it for nearly a century. But the truth remains, patient and persistent, waiting for someone to notice. Arthur Ruhlig noticed. And 87 years later, we finally understood what he was trying to tell us.